everybody. Welcome to course by Professor James Borger of the Australian National University on Witt vectors, arithmetic jet spaces, and algebraic groups. Jim, please begin.
Okay, thank you. Thanks for the invitation to speak here. It's really nice. Too bad I can't be in India itself, but these are the times we live in. So let me share my screen. Okay, is that all right for everyone?
Yes.
Okay, look at my notes. Okay, so let me just say a few words to get started. So the goal, well, at least one way of putting, let's pretend this is the goal. It's some approximation to it. So if you have something like this finite group SLN FP, P is a prime number. This is of course the FP points, the group of FP points on the algebraic group SLN, of course. And as I think I said in the abstract, we're kind of beginning with the question, suppose you have this finite group, SLN of Z mod P to the RZ. Does this equal the FP points on an algebraic group? One thing that might give you some confidence that the answer is yes, is that if we kind of look at what you might call an equal characteristic version of the integers modulo P to the R. So say we take a polynomial ring and over FP and mod out by the ideal generated by T to the R, then this is also pretty obviously the set of FP points on an algebraic group, because you just give labels. I mean, right? You just you kind of have a coefficient and I guess it's R minus 1, and so on, and then you write out the determinant condition, and then that will define an algebraic variety. So this is indeed the set of FP points on an algebraic group. And in fact, like, you can even just for fun say what the dimension is. I guess the dimension will be Rn squared minus 1. So it's some very large algebraic group, and so we want to know, okay, so we were kind of successful here that we have a finite group, and we can view it in a not very surprising way as the set of rational points on an algebraic group, the FP rational points, and we're hoping to do the same thing for SLN of the integers modulo P to the R. So this is our question up here. Maybe I'll put a Q for question, and then the answer is yes. That's the whole point of these talks, and probably many of you have heard of this or have some familiarity with it. So this is done by what's, I think some time ago was called the Greenberg transform. I kind of feel that the term arithmetic jet space is maybe taking over from the older term Greenberg transform. And this involves in an important way the concept of Witt vectors, which will be kind of the beginning of my of these lectures. And probably many of you have a little bit of familiarity with Witt vectors, but one thing that I want to say is that the approach here will be, maybe I'd call it a non-traditional approach. And so we'll take these lectures, we'll be using a traditional approach, which I say is primarily due to Bouillon and Joyal. They both did some things kind of independently. And this is all involving the concept of what's called the delta ring. So delta rings, in fact, have kind of really even hit the big time recently with their role in prismatic cohomology. Maybe I'll just put that in brackets of Bargov Bott and Peter Schulze. Okay, so that's just.
There's just a quick question. Raghavan wants to know, what about this formula when n equals 1? I suppose he's talking about the Rn squared minus 1 dimensional.
Right. Oh, did I get it wrong? No, wait, no, this might be right. So that would be the power series, the truncated power series of length r, but they have to be invertible. So they have to have constant term. Sorry. No, sorry. I'm doing GL. Yeah. Right. So what is, I guess it's, yes, stupid me. Okay, thank you. I guess it's Rn squared minus 1. Right? Because, yeah, because SL, yeah, sorry. Is that better?
I think that's, yeah.
Yeah, okay, thank you. Okay, are there any other questions?
Actually, maybe you can just unmute and ask. It's probably a manageable.
I'm sorry?
It's a manageable size of people here, so maybe people can just unmute and ask questions.
Oh yes, of course that would be great if you think it's manageable. Then yeah, that's it's always fun to just make it a real conversation. Okay, yeah, maybe actually on that note, I should say that I'm well, I know quite a bit about Witt vectors and arithmetic jet spaces. Algebraic groups, I'm certainly not an expert on. So, well, we'll just sort of see how that goes. I'm not sure exactly how much I'll say about algebraic groups, even though that's the motivating question. Most of the time, I'll spend discussing these Witt vectors and arithmetic jet spaces, and then kind of eventually tie things in with algebraic groups. Okay, maybe I'll go to another page here. Okay, so now we can kind of begin the main part. So the first section is on what are called p derivations and delta rings. So in all of this, p will be a fixed prime number. So you can fix it once and for all, really. And R will be a ring. And for me, my ring, by the term ring, I always mean commutative and with a multiplicative identity 1. Then here's one of the, maybe the 2 key definitions. A ring endomorphism phi from R to R is a Frobenius lift. Well, if it's exactly that. So if for all x in R, 5x is congruent to x to the p, need more space. Mod PR. So it's just congruent to the usual p power Frobenius map modulo p. Actually, let me say, even before, like this can kind of be changed. You could also look at Frobenius, replace the p in the exponent here with a p squared or something like this, and then you would get a different theory, very closely related to what I'm about to describe, but not literally the same thing. It's also possible. Yes?
What examples of R can we keep in mind?
Sorry?
There's some examples of R that we should keep in mind.
Yes. Yeah. So I have a whole bunch of them. So for instance, you could just take polynomials in one variable, and then you could, an endomorphism is described what it does on the generator, and then you can just send it to x to the p plus p times anything you want, like. So that will be, right, that defines a unique endomorphism, and obviously, so to verify this this congruence condition, you only need to do it on a set of generators. So this is on this generator X, it's obviously has the congruence property, and so that's it. So in fact, you can also do this with polynomials in any number of variables, even infinitely many if you like. In particular, you can do it with polynomials in zero variables. And that, of course, phi has to be the identity. The integers have only the identity endomorphism. But it is still a Frobenius lift because, well, if you like, it's Fermat's little theorem. That's one way of thinking about it. Okay, so what's another example? Just to show that there's maybe a little bit of arithmetic content. Suppose you take the Gaussian integers, then phi is, there are two possibilities. If p is congruent to 1 mod 4, then the identity is a Frobenius lift modulo p, and if p is congruent to 3 mod 4, then complex conjugation is a Frobenius lift modulo p. And if p is 2, then there is no Frobenius lift. So if p is 2, no Frobenius lift. So that's a little exercise. If you kind of know a little bit of algebraic number theory, like a very little bit, it would just be 1 or 2 lines. So it's not a hard exercise. So more generally, the subject of class field theory, in either local or global, especially global class field theory, you study these Frobenius elements of the Galois, the Galois group of a finite abelian extension, and they're on the at least on the ring of integers, the ring of algebraic integers in your number field. These Frobenius automorphisms do give Frobenius lifts. Let me just drop a few names. So also in crystalline cohomology, rings with Frobenius lift are pervasive. So I won't say anything more about crystalline cohomology. That's the last I'll say. And also in algebraic K theory, if you have a ring which is K0 of some, let me just say, a reasonable tensor category, like category of vector bundles on a manifold or locally free sheaves of finite rank on a scheme, then it has a certain natural operations called the Adams operations. And that gives you a ring endomorphism of the ring, the Grothendieck ring of the category C, and these are also Frobenius lifts. Okay, so this is just this will come up maybe once or twice again, but only in a way, not in a serious way, just to kind of shed light on some things. These won't come up at all anymore. These are kind of these are good examples to keep in mind, just using a bunch of polynomials in some number of variables. Okay, and now the goal of the first part of these lectures is that this all leads essentially formally to the concept of Witt vectors and arithmetic jet spaces and so on. So in a certain sense, if you're wise enough, once you kind of start thinking about the concept of Frobenius lifts, then almost everything else I'm going to say, at least for the next lecture or two, is kind of inevitable. So I guess the reason why I'm emphasizing this is that usually when you open up a book and read about Witt vectors, there are formulas everywhere. It's huge polynomials and big sums and big congruence conditions and all these things like that. And it kind of looks, on the one hand, very arbitrary, because where did all these random formulas come from? But on the same time, you get the feeling that everything works out so perfectly. Maybe there's some kind of hidden, it's not as, the formulas aren't as arbitrary as you might think. So what I'm going to do is give you this, a development of the theory that kind of, at least in my opinion, makes everything seem kind of inevitable. And the only ingredient that is kind of arbitrary is just the concept of a lift of Frobenius map, which I hope you'll agree is actually a very natural concept. So kind of makes, to me, it makes the whole development of the theory of Witt vectors seem very natural. Okay, so right, so now here's the second point is, if you look at the set of rings with Frobenius lift, equipped with the Frobenius lift, this forms a category in a natural way. The object an object is a ring together with a Frobenius lift, and a morphism in that category is a ring homomorphism, which is equivariant with respect to these two Frobenius lifts, which is such that the corresponding diagram commutes. But the key thing is that the category is not a good one. And why is that? So the problem is that the word lift has a hidden existential quantifier, which causes problems. So what is, let me just write what the definition of Frobenius lift is. It's, again, it's for all x, there exists an x prime such that 5x equals x to the p plus p x prime. So the congruence condition kind of hid this existential quantifier, but it's really there. And so the x prime is unique only up to p torsion. I mean, kind of obviously, right? If you add to x prime any element which is a p torsion element, then this equation will still hold. And conversely, if you have two different x primes that both satisfy that equation, their difference between them will be a p torsion element. But this was a big problem for us because we have no control over it if our ring R is not p torsion free. So all the examples I gave above, at least the explicit ones, were examples where the ring was p torsion free. But certainly you don't have to have rings with a Frobenius lift, which are p torsion free. Well, maybe I should have given you another one here. So let's actually, another one is another example would be any FP algebra. And then the Frobenius lift is actually just the Frobenius map, the pth power map. Maybe I'll, that's an important enough example, I'll add it in. And in that case, x prime is arbitrary because p is 0. Okay, so what's the solution? So the solution to our problem is we provide x prime as part of the structure rather than its mere existence, rather than the property of its mere existence. So we had a property that something exists before, and now we're going to provide it as part of the data. Okay, so i.e. we want to instead we'll take the Frobenius-Lift condition, the Frobenius-Lift property, and replace it with the structure of a map, a set map, which is modeled on this, which is kind of right. If you like, this is x prime, and that makes sense when the ring is p torsion free, because this quotient is uniquely determined. But now we somehow want an actual operator, which is kind of modeled on this. So what does that mean? Actually, one thing I wanted to say that now I just realized I forgot. So here's a little exercise. Exercise 1, the category of rings with Frobenius-Lift it's not entirely bad. It has all co-limits. So if you know a bit about the language of category theory, so this by this I mean coproducts. So that's arbitrary tensor products, direct limits. So direct limits. It also has co-equalizers. So these are all examples of co-limits, and in fact, if you have all of these, you'll have all co-limits by combining them. It also has all products. So if you take the product of two rings with Frobenius-Lift in an obvious way, the resulting ring has an endomorphism which lifts Frobenius, but not all limits. So I believe, although I would have to, I always have to think about this for a few minutes to work out another example. So I believe it doesn't have equalizers, it doesn't have inverse limits, and I believe it doesn't have intersections of subobjects. And the point is that, yeah, if this x prime is not uniquely determined, then things can kind of go wrong. If you say have two different subrings, an x prime on one and you have an x prime on the other, doesn't mean that those x primes actually live in the intersection. For instance, if we're talking about intersections. Okay, so what are the axioms? So what now I'm going back to here, what does it mean to have an operator modeled on this? Well, what I mean is we just write out the ring endomorphism axioms of phi, but in terms of delta. So somehow the point is that we want our delta won't be additive or anything like that, but we do want the map, the self map phi defined in terms of delta to be a ring endomorphism. The whole point is we want to talk about Frobenius lifts, but we want to do it in an intelligent way, which is a little more intelligent than what we did on the previous page. So okay, so how do you do this? So let's say we just take the additivity axiom. Okay, that's that. And now we just write it in terms of delta. So this is x plus y to the p plus p delta x plus y. And this side is x to the p plus p delta of x plus y to the p plus p delta of y. And now we rewrite this. So this is equivalent to the following. So it's equivalent to that. And now we notice that we can divide through by p. Obviously, we can divide through, I mean, at least syntactically, symbolically, you can divide through by, we can get rid of that p, that p, that p. And this right here is a polynomial in x and y with integer coefficients, all of which are divisible by p. So we can, I'll write this, but I don't mean a logical implication. I just mean kind of gives rise to in kind of a syntactic way. And then this becomes the sum of binomial coefficients. So I obtained this by dividing by p, but the of course the logical implication goes in the other way. So if this is true, then after multiplying through by p, this is true, and the converse is true if and only if the ring is p torsion free. So this is well, I'll say it's an equivalent only under a p torsion free assumption. And of course that's good because the category of rings with Frobenius lift, if there is p torsion, is not well behaved. So we want a definition that agrees with it in the p torsion free context, but is actually slightly different from it in the presence of p torsion. So okay, so this will be this is our first axiom for delta. That's sort of what remains of the additivity axiom on phi. Now we continue in the same way with the other. So if we take multiplicativity, I'll do it a little faster now. So this is xy to the p plus p delta xy. This is x to the p plus p delta x times y to the p plus p delta y. And then if you multiply it out, you get p delta xy is equal to, so this is logical equivalence, right? This will cancel. So what do we get? We get p x to the p delta of y plus p delta of x y to the p plus p squared delta of x delta of y. And then we play the same game where we have a factor of p everywhere, so we can divide through and get our second axiom by divide through by p. We get delta of xy is x to the p delta of y plus delta of x y to the p plus p delta of x delta of y. And again, this is equivalent to the previous line only under the p torsion free assumption. Okay, and the third axiom, so is, okay, I guess this is kind of a redundant axiom, but let me write it out anyway. You'll get, I mean, well, I'll just write down what you get. You get the delta of 0 is 0. So you get, well, we would have p times delta of 0 is 0, and then we divide through by p, and we get that. And the last ring endomorphism axiom, which isn't redundant, is that one. And that would give us that p of delta of 1 is 0. And then if we divide through by p, we play the same game that we've done before, and we get that axiom. So these are our 4 axioms for a p derivation. So maybe I'll put it here. Definition, function delta from R to R is a p derivation if 1 through 4 fold. So these for all, obviously, I mean, for all x and y in the ring R. So you'll note, why is it called a p derivation? It's because the second axiom, let me change colors here. This is sort of similar to the usual Leibniz rule for an actual derivation. So in fact, modulo p, what do we get? We get delta of xy is congruent to x to the p delta y plus delta x y to the p. This is mod PR. And this literally is a Frobenius twisted derivation. It's the usual Leibniz rule twisted by p. Okay, so it's reasonable to call them p derivations. In fact, what I'd like to call all of these 4 axioms here, I'd like to call them Leibniz rules for delta with respect to, now we have addition, multiplication, and then if you like 0 and 1. But the point is really addition. So unlike with usual derivatives, which are additive, p derivations are not additive, and they have their own Leibniz rule. This Leibniz rule up here, it's defined by a universal formula. Well, okay, it is what it is. Okay. One last comment before I keep going is that Boehm, in fact, likes to think of delta as the derivative with respect to a prime number. So, for instance, on the ring of integers, right? On Z, the Frobenius lift is the identity map. So so delta of n is just this, what you might call the Fermat quotient. It's an integer by Fermat's little theorem. And he likes to think of that as the derivative of the integer n with respect to the prime number p. It's a little silly, but not nearly as silly as you might think. There's really kind of a lot of, it's actually a pretty reasonable way of looking at things.
I mean, it's the derivative of the Frobenius map, right?
I wouldn't say it exactly that way. I mean, it's the difference between the Frobenius endomorphism. I mean, on the integers, the Frobenius maps the identity. So is the derivative of the identity. You wouldn't say the derivative of the identity is given by this delta. I mean, the Frobenius, okay. Maybe it depends what you mean by Frobenius map. If you mean the Frobenius lift, the endomorphism, it's somehow it's the difference between the Frobenius lift and right. So delta of x is 5x minus x to the p on p. So you have kind of the Frobenius lift, and then kind of maybe just the naive p power map, and it's sort of their difference.
Okay, so it's mentioning how far phi x is from the.
Right, and of course the p power map in characteristic 0 is never a ring endomorphism, unless you're on the 0 ring or something. So this will always be something non-trivial. Like, so you can't, okay, that's a good exercise. Let me go to the next page. I carefully numbered my exercises, so I'm going to call this, I'll call this 1B. I think the following is true. So prove or disprove that what was it going to be? Yeah, if delta is a p derivation and the zero map and 0, then the ring R is the zero ring. I would guess this is probably true. So this is something which is certainly the analog for normal derivations is certainly not true. On any ring, the zero map is a derivation, but not for p derivations. So I'd have to think about this, but I would be surprised if this were not true. Okay, are there any other questions? So I'm going to give lots of examples and a lot more exercises.
If R is an FP algebra, then the delta is 0, right?
No. So here's exercise 2. So if R is an FP algebra, admitting a p derivation, implies that R is 0. So the only FP algebra so FP algebras do not admit p derivations unless they're actually the zero ring. And so maybe I'll say, whereas all such R have Frobenius lifts.
You mean a non-trivial p derivation?
What do you mean by trivial?
No, I mean a Frobenius lift on an FP algebra is just x, p of x is x to the power p, which means delta is 0.
No, okay, so let's do p equals 2. So then we get that delta of 1 plus 1 on the one hand is equal to delta of 0, which is 0, but on the other hand, it's delta of 1 plus delta of 1 minus, now we have to do this Pascal's triangle thing up here, right? So we get a sum of length 1, and it's, so what it will be is 1 times 1. And then this, delta of 1 is of course 0, so we get 0 plus 0 minus 1. So we get, so therefore 0 equals 1. If, therefore the ring is the 0 ring.
Okay, so delta equals 0 will not satisfy.
Yeah, it's funny, but it's very non-additive. But if you think about it, it has to be very non-additive. If we're going to use this kind of theory to start with something in characteristic P, as I discussed at the beginning, kind of an algebraic group in characteristic P, and somehow make out of that something which is kind of in characteristic 0, or at least close to being in characteristic 0, you're going to have to mess with the additivity in a very fundamental way. So it's kind of an exotic construction, but it kind of has to be. Okay, are there any other questions on this part? Oh, I have to keep an eye on the time. Okay, let's see, what else did I want to say? Okay, so here's some important examples, which are kind of obvious. So if you look at the set of p derivations on R, and we alternatively look at the set of Frobenius lifts on R, there's a map between them to any p derivation delta you associate to it the endomorphism, which is defined in the obvious way, where 5x equals x to the p plus p delta of x. And this is, this is kind of obviously a ring homomorphism, because exactly the axioms for delta were designed to imply that it would be. In fact, they're a little stronger. So the kind of the point is, this is a bijection if R is p torsion free, but not in general. And that's kind of the whole point. It's not in general. Okay, so therefore, let's give some examples now. So if R is if R is, so any p torsion free, let's put it this way, this is an example of a ring with a p derivation. Oh, maybe I forgot to say that. Let me add that. So definition: a delta ring is a ring R equipped with a p derivation. So it's a pair, right? Formally, it's a pair consisting of a ring and a p derivation on that ring. So any p torsion free ring with a Frobenius lift is an example of a delta ring. So for instance, if we did this one before, and now remember phi before sent x to the p plus p times anything, but we could just write that now as delta of x. It can be anything. Another example, which I think this is the last time I'll mention K-theory. So if we take the Grothendieck ring of some symmetric tensor category, maybe you need some other hypotheses, I'm not sure. Then if you know a little bit about the theory of lambda rings, then you can, let me just put it this way. It's so delta is the lambda operation associated to the symmetric function, the following symmetric function in infinitely many variables. Okay, so if you know about lambda rings and symmetric functions, you'll know what I mean by this. If you don't worry about it. I won't mention it ever again. Okay, let me give a couple of more exercises. So that was, we got up to exercise 2. So now exercise 3 is, in fact, this thing I said above for FP algebras is also true for Z mod P to the NZ algebras. So if R is a Z mod P to the NZ algebra, admitting a p derivation, or I'll often just call it a delta structure, the structure of a delta ring on it, which is just the same thing as a p derivation, then R is the zero ring. So no non-zero rings in which p is nilpotent admit a delta structure. So you be tempted to, yes?
So if the ring R is not p torsion free, then also this statement will be true? Like, is it just because it has a p torsion point? Is that the reason? Or
Say that again.
So I'm saying you said this for FP algebra and Z mod P and Z, both of these have p torsion. So is it in general if the ring has p torsion? So and no, it's not.
That's a fair question. You might say I solved my problem with p torsion. Maybe I just solved it by ruling out all possible p torsion, and but that's not true. So say we have this example, right? So this is just z direct sum fpx, where x squared is 0. So certainly there's non-trivial p torsion. Then there is a unique p derivation satisfying delta x equals 0. So that's the exercise. Prove that, like, it's kind of obviously unique because this ring has it's generated by one element x. So once you specify it on x, there's at most one choice, at most one way of extending it to the rest of the ring. But what you have to prove is the existence, which, so you somehow have, I mean, there are kind of smarter and less smart ways of doing it, but you could just imagine writing out a formula for an arbitrary element, you know, a plus bx, and then expanding it and checking it. So this is not completely trivial. You have to really do something. Kind of the more theory you know, the easier it will be. But because also, you know, you want to define a well-defined operator on this quotient ring, but your operator is not additive. So the obvious thing to do, if it were additive, would be to somehow define it on the so to speak, on the numerator, on the original ring, and then prove that it vanishes on the ideal and therefore descends to the quotient. But it's not an additive operator, so you can't do that. So you somehow have to really, it's kind of fun in doing these exercises. You almost feel like you're a first-year algebra student just coming to grips with kind of just what these things mean. Okay. So one remark before I go on to the Witt vectors is that there is a formula-free way of saying all this. So I said in the beginning that I wanted to give you an approach to Witt vectors without using formulas, and then the first thing I did was write down a bunch of formulas. However, it's not really necessary. In this approach, it's not strictly necessary to write down the formulas. It's somehow, it's just that it's actually more clarifying to do it. If I tried to give an approach without using any formulas, it would just feel a little bit like I was avoiding saying something in a very simple way because I didn't want to write down a formula, which would be true. But I mean, maybe later in these lectures, I could talk about how you might do this. But I think in the beginning, it's best just to use the formulas, even though eventually they kind of can disappear. Okay, I wanted to say one more thing, which I think I forgot to put in my notes, but it just occurs to me. So here's another exercise. I'll call it 4B. So, but again, I mean, I'm certain it's true, but since I haven't gone through the trouble to kind of write it down and think about all the steps, I'll just say prove or disprove. Well, I guess the first step is to formulate it properly, precisely. The identities that delta satisfies for p torsion free rings are generated by 1 through 4. So what do I mean? Maybe sorry, let me just put it this way: that phi of x. Let's do it this way. That phi of x minus x to the p on p, that this operator satisfies for p torsion-free rings with Frobenius-Lift phi are generated by 1 through 4. So what I believe is true is that these, I mean, this is how you would kind of do it if you were going to do a formula-free way of saying it. You would say you want to look at all the relations that such an operator would satisfy if you restrict to p torsion-free rings with Frobenius-Lift, and then you would call that you would call that structure a delta ring structure, and then you would prove that in fact those identities are somehow generated by the simple ones we wrote down above with the formulas. Yeah, maybe that wasn't so clear. I don't know if there are any questions.
So
Okay.
this
Yes.
exercise is sort of the non-trivial part of saying that there is a formula-free way of this.
Non-trivial part of what?
Of the assertion that there is a formula-free way of saying all this.
What about that assertion?
That means that you lose nothing by only specifying these 4 axioms, right? I mean,
Yeah, that's right. Or yeah, that's right. You get, yeah. Somebody might be tempted to say, okay, there are many identities in terms of universal formulas that such a delta would satisfy. Like, why do you only look at these basic ones? There are probably more complicated ones for like delta of x squared. Why? And the point is, I'm sure it's true, although I haven't checked it myself, that these basic ones involving addition, multiplication, 0, and 1, I mean, because everything in a ring, because a polynomial expression is somehow generated by addition, multiplication, and 0 and 1, any identity that delta satisfied in the p torsion-free setting would come from these basic ones. Okay, so now let's go to Witt vectors. Okay, so how are we doing? Okay, we don't have tons of time. So here, what's the goal? The goal for the Witt vector part is that, so we have the category of delta rings, and then we have the category of all rings, and there's a forgetful functor, which I've drawn here. And the point is that the Witt vector functor is the right adjoint of the forgetful functor. So if I'll explain what that means. If you don't know the basic language of category theory, that's all right. It's just a simple property, I'll tell you. In fact, there's also a left adjoint. So they write that like that. And we'll talk about that as well. So what I'd like you to do, this is meant to give an explanation. Somehow I hope I've convinced you that the concept of a delta ring is kind of formally inevitable once you say the phrase Frobenius-Lift. And then just by doing a little bit of category theory, the Witt vector construction is also formally inevitable because it's just the right adjoint of this forgetful functor. So let me just explain to you that this setup is something very should be very familiar to all of you. So let's just compare this with, say C is a ring, which maybe now can even be non-commutative. You have the category of C modules, and then you have the category of abelian groups. The left adjoint of the forgetful functor is the tensor product functor, and the right adjoint of the forgetful functor is the Homs, is this functor. So this, you might call this one the co-induced C module, sorry, the induced C module, and this one the co-induced C module. Also, if there's a kind of a discrete version as well. So you could take, say you have a group G, you could have G sets, you have a forgetful functor to sets, then you have a left adjoint, which is just the free G set generated by a given set. So you just take the product with G, which you could also say is the disjoint union of G copies of your set. And then the right adjoint is the analogous thing, but instead of the coproduct of G copies, it's the product of G copies of your set. And then G acts, of course, G acts on this set via its action here, G acts on this set via its action here, or equivalent its action there. So, so what I claim is that that W is kind of an analog of either this construction or this construction, but in this slightly more messier context. So in fact, the analogy I really want to emphasize is differential rings. So by a differential ring, I mean a ring equipped with a derivation in the usual sense. And there's a forgetful functor from differential rings to rings. And this will also have a left adjoint and a right adjoint, which are maybe, well, they're not that hard to say. It's not that hard to say what they are, but maybe it takes a few more words than in the case of modules and G sets that I just discussed. So let me call this one the differential Witt vectors. So this is a something I invented, just this term. It's a construction that will be very familiar. So what is it? So W diff of A is just the set of divided power series with coefficients in A. So it's the set of sums which look like this. Now, this right here should be viewed as just a formal symbol. It's a placeholder. So I'm not stating anything about actually dividing by the integer n factorial. I'm not assuming characteristic 0 or anything like that. It's just a symbol. But the purpose of that symbol is that it has the obvious ring structure. So, so the obvious ring structure, should I write it down? So t to the m on m factorial times t to the n on n factorial is m plus n, choose n, times t to the m plus n on m plus n factorial. Okay, that maybe is not so clear, but I hope it's not so visible, but I hope the mathematics is clear. And then and the derivation is just the derivative with respect to t, the kind of the formal derivative, which is just a shift. You're just shifting coefficients. So right, so it takes t to the n on n factorial to t to the n minus 1 on n minus 1 factorial. So this is that's a differential ring. So this is certainly a well-defined functor. And it has a universal property, which is exactly the right adjoint universal properties, but let me just spell it out. Okay, so suppose you have a ring R, but now it won't be a delta ring, it will be a ring with a derivation. And in a few minutes, it'll become a delta ring, but not yet. And suppose you have a ring homomorphism to another, to just a ring A, which it's just a ring. Then you have the ring of the so-called ring of differential Witt vectors. You have a projection map, which just sends a power series to its constant term, its value at 0, if you like. And now I claim that there exists a unique lift here, which I'll call G tilde, a unique lift which is D equivariant. So it's a homomorphism of differential rings. And in fact, it's easy to say what it is. So G tilde of an element R is you so to speak, you have a derivation here, right? So you can kind of formally take a Taylor series of R, and that will have coefficients in R, and then you just apply G to all the coefficients and get a Taylor series with coefficients in A. So I'll say G of the Taylor series of R. So that's that. What do I really mean? I just mean the sum of G of the nth derivative of R times t to the n on n factorial So this is, let's just make sure that makes sense. The nth derivative of R is still an element of R. We apply G to it, we get an element of A. So this is a divided power series with coefficients in A. So that's what a differential bit vector is. So that's a perfectly well-defined thing. And yeah, so then you kind of want to check that G tilde is a differential ring map and the unique d-equivariant lift of G. So intuitively, what is this? The reason this is true is because, why is it a ring map? Because the Taylor series of a product is the product of the Taylor series of the two factors. So that I guess that's maybe a theorem. And
I just was distracted for a second. What is this DOU?
That is the nth iterate. Yeah. Okay. Thanks for asking. I'll use
Supposing, okay, the nth iterate. Yeah.
yeah. So D circle N is decomposed.
D circle.
Yeah, so it's a multiplicative map simply because the Taylor series of a product is the product of the Taylor series. It's d-equivariant because the derivative, the formal derivative of the Taylor series is just the Taylor series of the derivative of a function. So that's why that's true. So this is exactly the adjunction. This is the right adjoint universal property, that the set of ring maps from a differential ring to a ring A are in bijection with the set of differential ring maps from the original differential ring to the differential bit vectors of A. So maybe should I write that down? So we look bijection between these are, say, diff for the set of differential maps, differential ring maps. So that's another way of saying this universal property, which is just another way of saying the right adjoint property that I mentioned before. Okay, so you should be thinking of it. Soon we're going to go to actual bit vectors and delta rings instead of differential rings. But before I do that, let me say one more thing. So here's an alternative point of view. That the differential bit vectors of A, you can just, it's just a vector of such a divided power series is just a vector of coefficients, right? You can just think of this as just being the vector A0, A1, A2, and so on. As I said before, this is just a formal symbol. And then the derivative is just the shift left. Right, shift left. And then this map G tilde, in these terms, it just sends R to the vector of all the derivatives of R mapped to A. So it's just it's G of R, G of the derivative of R, G of the second derivative of R, and so on. So that is exactly, remember, right here, the coefficients are just given by G of all the derivatives of R. It's exactly what I wrote down here. And now it's maybe kind of obvious that, so in fact, G tilde is the unique set map, the unique d-equivariant set map lifting G, because because if it lifts G, the constant term of this power series better be just G of R. In other words, the the component number 0 here has to be G of R, but then it also has to be D equivariant. So then D is just a shifting operator on these coefficients. So if you take this vector and then shift, it has to be the same as that if you first applied the derivative to R and then made the corresponding vector there. So you just get that all the other terms are exactly as written. So in fact, G tilde is the unique D equivariant set map lifting G. And so therefore, from this point of view, so I haven't even mentioned the ring structure on the power series. The ring structure on W diff of A is forced, is the one forcing, it's the unique one forcing G tilde to be a ring map. And in fact, like I'm kind of speaking abstractly here, but in fact, it's a very concrete thing. In fact, the ring structure on W diff A, if we think about these things as vectors rather than as power series, is a, I'll put it this way, a syntactic re-expression of the Leibniz rules for the derivative operator and all of the higher derivatives as well. So what do I mean? So you probably did an exercise in first year that to come up with a formula for the second derivative of a product, for the third derivative of a product, and so on. So let's just write this down. So if you take the product of two power series, of course, this is the product over AI bj, I plus j, choose I, times t to the I plus j over I plus j factorial. And therefore, when you multiply these two power series together, but now I'm doing the same thing, but just writing them as vectors. The nth component of the product is simply the sum over I plus j equals n of n choose I times ai bj. But now notice that the formula for the nth derivative of a product is really the same formula. It's the ith derivative of x times the jth derivative of y, and we sum up over all I and j such that I plus j equals n, and then you need a binomial coefficient. But the point is that this is a polynomial expression in the derivatives of I and the derivatives of j, and this is a polynomial expression in the AIs and BJ, and it's the same polynomial, just evaluated on different things. Okay, so now we can go back to the actual. So even if we hadn't been so clever, it didn't require so much cleverness, but to think of these power series here, I claim that actually it would have been entirely forced on us by just thinking about vectors, and then we have a shift operator, which is our derivation, and then the ring structure is entirely forced by the Leibniz rules for the iterates of our derivative operator. Okay, so now I'm ready to go back to W, the actual bit vectors, but maybe I can see if there are questions before I do. So. Okay, so we do the same thing, the only difference is that now our delta operator has a Leibniz rule. It's not additive, so there's a Leibniz rule for addition and for multiplication. But other than that, everything is the same. So so we'll define W of A, the actual vectors of A, to be at this infinite product. And now the ring structure on this infinite product at the nth component, so to speak, is given by the Leibniz rules for the nth iterate of delta with respect to both addition and multiplication. So when I say ring structure, the additive part of the ring structure is given by the one corresponding to addition, and the multiplicative part is given by the one corresponding to multiplication. So we can just write out what these are for the first, at least the first two components. So, so component number 0 is, that's the 0th iterate of delta, which just means the identity map. So the identity map is both additive and multiplicative. So that part is easy. So the fact that it's the additivity of the identity operator corresponds to that formula, the multiplicativity corresponds to this formula. Now, for these parts, we have to write in the formulas for the Leibniz rule for the first iterate of delta, in other words, the actual delta operator with respect to addition and then multiplication. So let's go back. I remember these, but I figure you guys probably don't. Okay. So this is our formula. So somehow, let me just write out the answer and you'll see how I get it. So it's A1 plus B1, that corresponds. If delta was additive, it would just, that would be the end of it. And then our formula would end here. But now we have these error terms, and how they come in are exactly like this. Of course, all these are integers. I should have said that before. Everybody knows it, but those are all integers. Okay, and then I could ask if anyone wants to guess the formula for the multiplicative one. It's somehow, I claim it's just a syntactic way of reformulating this right here. And does anyone want to guess it? Okay, I'll just write it.
A1, B1.
Sorry?
Minus, I guess, P times A1. What?
I missed it at the beginning, so but you're probably right. It's A0 to the P times B1 plus A1 times B0.
Minus P times.
Well, there's no minus signs down here, so they won't.
Oh,
so
yeah,
this,
yeah. So it's just P times A0. A1.
So it's just that. It's exactly the same polynomial, but now I'm going to delete these. Just evaluated at, instead of at the sequence of derivatives, it's evaluated at the sequence of components. So more generally, nth component of the sum is, I'll write it this way, Pn plus of A0, B0, comma, dot, 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 comma, An, Bn, where Pn plus is, this is now a polynomial with integer coefficients. In, I guess, 2n plus 2 variables, where this is the Leibniz rule for the nth iterate of delta with respect to addition, in this following sense, that the nth derivative of a sum is a certain polynomial expression in all of the lower derivatives, the lower order derivatives of the two summings. And okay, so and similarly for multiplication. So it will be a different polynomial, which I would call Pn times, and that would be for the Leibniz rule for the nth iterate of delta with respect to multiplication. So these polynomials certainly exist because you can just, to compute the sum, the nth derivative of a sum, you just, first you take the first derivative, you apply delta once, you get some massive polynomial, then you apply it again, you get some even bigger polynomial, and you keep doing it n times. One thing that has to be checked, however, is that, I think this is exercise 5, check that Pn plus and Pn times are unique. So conceivably, it could be that there are two different polynomials that both give you the Leibniz, the appropriate Leibniz rule. And the way you prove this is that you reduce to the p torsion free case. So maybe I'll leave that exercise at that. I should also say that just in terms of the ring structure on, so these are the Witt vectors. I've just told you the ring structure on the Witt vectors. So Witt vectors are just vectors. They're vectors of infinite length. Of course, you can also look at Witt vectors of finite length, but these are Witt vectors of infinite length. And the ring structure is defined in this way, which is, I guess, a little bit implicit. The zero, I haven't told you the zero. That's so the zero is just all zeros, and that's because that's just a syntactic reformulation of that Leibniz rule, if you like. And the multiplicative unit is that, and that's a reformulation of. You'll recall that the nth iterate of delta, when applied, well, delta of 1 is 0. That was one of our axioms. So then delta of 1 is also 0, and so on. So more generally, the nth iterate of delta is this is now the Kronecker delta function. So this is just kind of another way of saying it's another way of syntactically encoding that axiom. Okay, and now maybe the last thing I'll say is the universal property. So the universal property for the usual Witt vectors, well, it's the same one. So what do we have? We have now a delta ring R. We have a ring homomorphism G to just some ring A, and we have the ring of Witt vectors. Oh, I didn't tell you. I forgot to tell you delta. So delta is just the shift, just like with the derivative in back when we were doing differential Witt vectors up here. Remember, yeah, this is taking the derivative was just shifting the vector of coefficients of the power series. So that's what delta does the same thing here. We have delta, and the property is that there exists a unique lift, which is delta equivariant. So G tilde of R, just as before, will be the vector consisting of G of all the derivatives oops. So G tilde is as before, it's the unique delta equivariant lift of G, and it's also a ring map by construction of the ring structure on W of A. W of A was the ring structure was constructed exactly to make that map delta equivariant. So therefore, we have a bijection between the delta ring homomorphisms from R to WA and the ring homomorphisms from R to A. So R is of course a delta ring, A is just a ring. So we have a bijection, and that just means, i.e., W is the right adjoint of the forgetful functor of delta rings. So that's the universal property. Okay, the last thing I want to say is a warning. So our W is canonically isomorphic to the usual Witt vector construction that you'll read about in the books, for instance, Sari's local field book or Bourbaki, but not by the identity map. So even though if you read the books on Witt vectors, the ring of Witt vectors is defined to be the set of vectors of infinite length together with some exotic addition and multiplication operations, just like ours was, but the exotic addition and multiplication operations, they agree in the first two components, but they differ beyond that. So the traditional plus and times differ at n equals 2 and beyond. So that might sound kind of weird, but actually it makes a lot of sense. But that's what I'll start talking about next time. Okay, so that's the end of the first lecture. Are there? I'll ask for questions, but also if you're more than welcome to email me a question or a question or requests for maybe things that I could clarify in the next lecture. But yeah, are there any questions now?
I have a question that, I mean, how can I is there some specific property for a ring that I should look for if I want to know it has a p derivation or not? Like, is there something other than, I mean, is there something that or says it cannot have a p derivation? Something, are there things that one can look for?
I think if it's smooth over, I mean, first of all, it needs to have an endomorphism, except in degenerate cases, this Frobenius lift will not be an automorphism because it'll be kind of degree p because it needs to have an endomorphism, which is not an automorphism. So I guess kind of most ring, so if p is invertible, okay, so so any Z join 1 on P algebra R has a delta structure, and then you can just take the Frobenius lift to be the identity, and it's p torsion free. R is p torsion free, so putting a delta structure is equivalent to giving it a Frobenius lift. But when you quotient this ring by p, you get the zero ring if p is invertible. So the Frobenius lift condition is vacuous. So the Frobenius. So this is maybe I'll just say it this way: phi can be any endomorphism, any ring endomorphism, because the Frobenius lift condition is vacuous. So that is so if p is invertible, I think your question becomes uninteresting. So now, what if p is not invertible? Then it's a real condition. So for instance, if in algebraic geometry, most varieties, kind of varieties more in the direction of being of general type, don't have non-trivial endomorphisms. Like a curve of genus 2 or more can't have non-constant endomorphisms by the Hurwitz genus formula. So if, of course, if you are on a projective space or an elliptic curve or something like this, then of course you can have you can have endomorphisms which are not isomorphisms, absolutely. But somehow, if your rings are so somehow maybe the closer your ring is to being something like a polynomial ring, I guess if your ring is far from being a polynomial ring, then it probably won't even have a non-trivial endomorphism at all. And if P is not invertible, this is not a theorem, but kind of at least philosophically, the Frobenius lift won't be. Well, yeah, no. If the Frobenius lift is an isomorphism, then the pth power map modulo P is an isomorphism, which would mean that the ring modulo P would have to be a perfect ring, which is, so if it's a finitely generated ring, that won't happen unless it's something like a product of finite fields or something like that. Yeah, things that are very close to okay, you can have other ones though. If you were in algebra, say you had a Z mod P squared Z algebra R, then and if it's I know this isn't an algebraic geometry, but a thing crowd. But if it's formally smooth, then probably it will admit a Frobenius lift because yeah, what do you want to do? So you have like R mod PR. This is the usual Frobenius map, and then you have are here, and then this is take me a second. So we want to know if there exists. Of course, if it's yeah, it won't have a delta structure. But I guess I'm wondering if it just has a Frobenius left, and I think it will, because so what is the? Oh, right. We need right. Let's try it again. So R is over Z mod P squared, and then that's formally smooth, and then you have, I guess, R modulo. Where do we want? Yeah, so that's just the quotient map, and then this. What am I doing? Oh yeah, goes the other way. And then this would be the projection composed with the Frobenius, and then the formal smoothness property would say that there exists a map here making the diagram commute. So then that will be a Frobenius lift on R, and then you can continue mod P cubed, mod P to the 4, and so on. So if you somehow have if R is, say, p-adically complete, and formally smooth over the p-adic integers, then I think probably it will have and then it will probably have a Frobenius lift, and I guess this ring will be p-torsion free, so it will also then have a delta structure.
So, okay, so I mean, one can cook up like derivations from these rings that don't have derivation to begin with. That's kind of what you're doing, right? So you started with Z mod P square, Z mod P cube. Those had, I mean, didn't have the derivation as such, but then you're like looking at inverse limit, and then it becomes like you're cooking up. Okay.
Yeah,
Okay.
I think the reason is that they kind of will have they will have this structure if you lose 1 power of P. So you can have just the usual projection, and then you can kind of have another map which you can call a delta. So the usual axioms will hold, but they're only going to hold mod P to the n-1, and then in the limit you get the two become the same. I think that's what will happen.
Interesting. So these are like the P torsion free kind of things. But if I have a P torsion, then also is there like one can do constructions of that nature with the derivation? Is there? I mean, I just a vague question. I'm just curious that what is happening. But yeah,
I don't know. So you want to so if R has P torsion in it, I mean, I guess formally smooth. Surely formally smooth will imply that will imply flat, and then therefore kind of in other words, somehow the torsion in R is kind of going to come only from torsion in Z mod P squared Z, and then I think in the limit it would still be P torsion free. Yeah, somehow the torsion, like the whole origin of the theory is actually in the, even though usually people care about taking the Witt vectors of things like FP, which are certainly not P torsion free. The whole origin of the theory is actually in the P torsion free context. All this whole game that we did with casting out factors of P, and the point is that then the interest of the theory is then in the extension of that to the context where there is torsion. So yeah, I guess somehow that I would say like the real, this is another good thing to say that I don't know about what really derived algebraic geometry is, but apparently a derived structure, a delta structure is the same thing as a derived Frobenius lift. So in the setting of derived algebraic geometry, if you just write down what Frobenius lift means, then it's exactly, so I understand, it's exactly equivalent to being a delta structure. So in a certain sense, this business about torsion, it's like the real story is in the p torsion free setting in my mind. Thank you.
So yeah, okay. We'll wait for if there are other questions.
So there's a question in the chat whether there are references that we could look at.
Yeah. Yeah. Okay. So maybe the historical references would be Joyal, André Joyal, the category theorist. He has one or two very short papers in the Compte Rendu. How do you spell Rendu? Of Quebec. Maybe in the early 80s. Bouillon, if you want notes for the something close to along the lines of what I'm saying, I have some notes from a class I gave in Copenhagen in 2016. So if you look on my web page, there's some lecture notes, good lecture notes taken by Lars Hesselholt, and with even lots of exercises. Also, the section 1 of my second paper with Lance Gurney. This is on the archive. I can't remember what the number is. We have two. It's the second one. And in the first section, we kind of review this point of view very quickly, but also from the very beginning. So people might like it because what I said today is maybe covered in the first 2 pages or something, and then what I'll say in the coming lectures maybe we'll cover the next couple of pages, but until I go to algebraic groups. Actually, might be able to find some other. Yeah, though that's really these are all the I think the best references. This Bouillon is maybe not. That will maybe come in more later when we get to the jet spaces. But Joyal's paper is very short, like maybe 4 pages.
6 pages or something.
6 pages, yeah, exactly. Yeah.
So historically, this adjoint characterization of bit vectors, is that due to Joyal or is that something?
Yes, that's it. So the simple answer is yes. It should have been noticed by some other people before him. Somehow, so to speak, the mathematical content behind it was already known in the older traditional approaches to the bit vectors, but nobody ever thought of. It was understood to have a right adjoint property under certain torsion-free assumptions, and the torsion-free assumptions kind of formally handle it in general, but nobody ever thought to make that conclusion. And also nobody ever thought to give this simple definition of a delta ring. So those were both due to Joyal. And so I mean, in some sense it's all pretty formal. Part of me wants to say like Joyal shouldn't get full credit because it's just formal, but on the other hand, the whole thing is formal. So like, of course he should get full credit. Right? The whole point is that he realized that it could be understood in this formal way.
I just wanted to mention that I've created a discussion forum and invited all the registered participants to that. Jim, if you like, I could send you an invitation to join that too.
Sure, yeah.
Questions can be, so everybody can see, the questions that are being asked.
Oh, I see. I haven't been looking at the chat, but
No, it's not on the chat. I'll do that.
Okay, but there are some other.
So it'll be a discussion forum because I think it'll take some time for, at least for me, to absorb everything you've said today. So we'll have a week to discuss it.
Yeah.
So there's a forum I've created and I'll be sending you a.
Okay, good. If you are going to think about, there are also, as I said, many exercises. So in particular, there's a whole sheet of 10 exercises for the first week of the class. So, yeah, anyway, there's more than enough if you are interested in really trying to become comfortable with these things at this webpage.